Okay, so good afternoon everyone. I welcome you back to my YouTube channel, and presenting before you this wonderful tutorial is Hampio Kliman. Okay, so today I will be teaching you Doppler effect. It's a very simple topic under chemistry, under physics rather, but there are certain concepts that you are supposed to know in order for you to find this topic very easy. So let's begin. So Doppler effect is simply all about the increasing sound, light, or vibration frequency. It can also be defined as the decreasing sound, light, vibration frequency, the decreasing sound, light, vibration frequency. Okay, so all in all, we are simply bringing out the frequency is our main center. The frequency happens to be our main center. So all you have to know about this topic is simply the relationship that is between the distance the speed and the frequency of an object. If you know the relationship that is between the distance, the speed, and the frequency of an object, this topic becomes very simple. What do I mean? So let's give an example. If we have person 1 here, okay, then we have person 2 standing here. We know that person 1 and person 2 are standing at some distance apart from each other, and this distance is simply meters. But at the same time, we know that if this guy begins to move in this direction, the distance is simply decreasing, but what is happening is the frequency of sound. We imagine that this guy is screaming. Okay, then this guy is hearing. Okay, we just say this guy is hearing the sound that person 1 is producing. So the more person 1 moves in this direction, the more person 2 hears the sound. Okay, but if we imagine that this guy moves in this direction, then it will happen that the frequency of sound this person will be hearing is going to decrease. But if this person moves in the positive direction, then it will happen that the frequency of sound will be increasing. So this particular concept that I've given right now is very important under this topic. Now, there are certain formulas that you're supposed to know, and these formulas, they depend accordingly to the movement of the object. Okay, so let me write something: movement of object. What do I mean by this particular point? So for example, if this is our person 1, okay, let's imagine that, okay, this is person 1, of course, person 1, then we're going to have another guy here. Don't really know how to draw, but of course it's making sense. Let's name this guy as person 2. So now, if this guy is traveling in this direction, okay, approaching this guy, then it simply means that this guy, okay, if we imagine that the guy is screaming, producing sound, then the frequency of sound that person 1 is producing is going to be called as the frequency of the source. Then the frequency of sound that person 2 is going to be hearing is going to be called the frequency of the observer. Now, this person is moving in this direction. Let's imagine that they have something in common in between. Okay, or let me just say, let's say there is God in between here. We put a diamond like that. Okay, so it will so happen that as this person moves in this direction, approaching this person here, you need to imagine that this person is also coming in this direction. Why do I say so? It will be very easy for you. Why? Because you know that this guy has a positive has a positive movement approaching the diamond, and this guy here also has a positive movement approaching the diamond. So in your mind, you have to know that this guy and this guy are approaching each other at this particular point. But when in the actual sense, it's this guy who is moving. Now, it's very important to understand this aspect. Why? Because whenever you have a situation, let me try to wrap this. Just a quick one. Okay. And just wrap this. Okay. Okay, even this anyway. Okay, so why am I saying that you understand it in that aspect? It's because whenever you have a situation, okay, let me write situation 1 here. Okay, let me say situation 1. So under situation 1, this is what we have here. Person 1 approaching person 2. Now, whenever, this is point number 1, whenever approach, okay, whenever approach is in the direction of observer, the formula that you use is the frequency of the observer over, remember that if you produce sound, this sound is traveling in the air in order to reach person 2. So you say that will be equal to V for the velocity of the air, for the velocity of sound in air, plus this is going to be the velocity of the observer. This must be equal to the frequency of the source over the velocity of sound in air plus the velocity of the source. So this is very simple. This formula is going to work every time you have an object approaching a particular object, and that object 1 must be producing the sound. It must be the source to the frequency of sound to the person 2, and person 2 must be the observer of that sound. So that's the concept that we're using here. It's very simple. Now let's get to try to talk about situation 2. Situation 2 is simply where you have object 1 moving away from object 2. So how about if we have, okay, we have these two people here, then we have, okay, then this one is person 1, person 2. Okay, we imagine that what they have in common is a diamond in between. Now instead of this guy moving in this direction, this time around he moves in this direction, opposite to person 1. So remember what I said? I said that whenever person A is moving toward person whenever person 1 is moving towards person 2, remember that they have something in common. Okay, they have something, sorry about that. They have something in common. So you imagine that this is positive and this is positive. But in this case, this guy is moving away from person 2. So you imagine that this will be negative, and even this guy, this will be negative. So whenever the approach towards the observer is away, the formula that you are going to use is this: the frequency of the observer over the sound, the frequency of sound in air, plus, now remember that the velocity this time around is very much negative because the person is moving away. So of course we're going to have negative V here, equal to the frequency of the source over the velocity of sound in air, plus, sorry, I made a mistake here. Supposed to be negative. Okay, whenever the approach is positive, supposed to be negative here. So, all right, even here, let me try to put my negative sign. So even here, it will be negative. So you're going to have negative V like that. So you use this formula whenever the approach is opposite to each other. So having known this concept, let's try to do some practice questions. Okay, So we have a very good question here. They're saying, okay, let me try to get another column so that you'll be able to see people. Okay, so they're saying two trains. So we're having two trains. We're having two trains. We're having two trains. Sorry. We're having two trains on separate tracks. Now, this particular statement is very important. Remember what I was teaching? This particular statement here is very important. They move toward each other. Train 1 has a speed of, this is supposed to be 130 kilometers per hour. Okay, so let me try to write my data. Let me try to write my data somewhere here. Let me try to write my data somewhere here. Okay, so we're going to say data. So they're saying train 1 has a speed of 130 kilometers per hour. So train 1, so the speed Vt all right. So train 1 has a speed of 130 kilometers per hour. Train 2 has a speed of 90 kilometers per hour. Then they're saying train 2 blows its horn, emitting a frequency of that. So train 2 in this case is the one which is making sound. So in this case, train 2 is the source. Okay? So we're going to say that. And what's the speed for train 2? Of course, the speed for train 2 is simply 90 kilometers per hour. So we're going to say that the speed, so Vs is equal to 90 kilometers per hour. Vo is equal to, let me try to punch that. So this is 1 point. Wait a minute, what is that? This is supposed to be 1.3 multiplied by 10 to the power 2. Of course, this is 130 kilometers per hour. So we're going to have 130 kilometers per hour. Okay, and of course, if we convert this to meters per second. How do we do that? If you want to do it very fast, you just, okay, so kilometer per hour to meters per second. If you want to do it very fast, just divide this by 3.6 and you get the answer here. So in this case we have 90. So 90 divided by 3.6, we're going to get 25. So this is 25. So this is 25 meters per second. 130 divided by 3.6. Of course, this is going to be 36. Okay. Then what was the frequency of the source? So the frequency of the source, we have been taught that it is 500 Hz. What is the frequency of the observer? I guess that's what we're looking for. Now, remember the situation. they are moving towards each other. So when they are moving towards each other, what formula do we use? Of course, frequency of the observer over the velocity of sound, of which velocity of sound in air is always 340, should be 342, okay, 342. So this is the velocity of sound in air, and of course this is going to be plus velocity of the observer, that will equal to the velocity of the source over VA minus VS. So we insert in the what we have. So in this case we're finding FO. So we have, this is going to be 342 plus, what is the velocity here? The velocity is simply 36.0. That will equal to Fs is 500 Hz over, this is going to be 342 minus, this is going to be 25. Okay. Let me try to clear my board. Now, we're going to have, this is going to be FO over, what is, this is 342 plus 36. This is going to be 378 equal to, and of course we have a 500 here over, so this is supposed to be 342 minus 625, and of course we get our 317. We cross multiply, we're going to have 317 FO equal to 500. So 500 multiplied by, this is 378. We're going to get something like, this is supposed to be this figure. Over 317, all over by 317. We cancel, we're going to remain with 5, and this makes sense. This is supposed to be 596.2 Hz. So this makes sense. Why? Because remember in my explanation I mentioned that when you have this person here and this person here, whenever you are moving in this direction, the frequency of sound that this person is going to be hearing will be increasing. So in the first place we had a 500 Hz. That's what the source was producing. But person 2 had a frequency of 596.2 Hz, which was quite high. So whenever you have an approach that is positive, this is going to happen. Okay, so we get to the second question. Of course, let me clear my board. Okay. Just a quick one. Okay, we get to the second question. So this question is simply saying a tuning fork vibrating at, okay, so we have a tuning fork vibrating at this frequency, then it falls from rest. So this guy falls, so this guy is going to make sound. So of course this is our source and accelerates at, I've been given the acceleration. How far below the point of release is the tuning fork? We imagine that the point of release is going to be the observer. Okay, so it's very simple if you imagine in those ways. Okay, it's very easy if you imagine in those ways. It becomes very, very much easy. All right. Let's correct our data. So we're going to imagine that the frequency of the source is 512 Hz. Okay, so I'll say my data here. So let me get my chalk. So I'll say data. So for A, the frequency of the source is 512 Hz. The frequency of the observer, we have been told that it is 485. 485. Sorry. The velocity okay, then we've been told that the acceleration is 9.8. So our acceleration in this case is 9.8 meters per second, and we know that the velocity of sound in air is always 342. Okay, 342 meters per second. Okay, so some books will say 342, 343, whichever you choose, it will work for you. Now, so in this case, we're going to use the other formula, not for the positive approach, but instead we use the formula for the negative approach. Why? Because it's not falling towards. Okay, it's falling away, if you understand the question. So in this case, we know that the frequency of the observer is over the velocity of sound in air plus the velocity of the observer. That will be equal to the frequency of the source over the velocity of sound in air minus the velocity of the source. Now remember that it's falling away. So if it's falling away, the formula changes. It shifts to this. I already talked about this in the first session, in the first lesson that we had. So in this case, we're going to have the frequency of the observer over, because it's falling away, so we're going to have a minus here equal to the frequency of the source over, so this guy is going to become positive this time around. Okay, so this is the formula that we're going to use. So now the frequency of the observer is simply 485. The question is simply asking us how far below the point. So how far is the distance? So that will be over. Now remember that we don't have this guy here. We only have this guy. So we're going to put our 3 43 here. What is the frequency of the source? It's 512. Okay. Then of course the velocity of sound in air is 343 plus, we have not been given the velocity of the source. So this is supposed to be source. We have not been given the velocity of the source, but probably that's what we're looking for. That's what we want to find. Why? Because we know that there is a relationship between velocity and distance. How does the relationship come about? Let me get my other chalk. You must always be able to think in these lines. How does the relationship come about? It's here. We say relationship for R. The relationship is V power 2 equal to U power 2 plus 2A H. So this is what we want. So in this case, we just want to find the velocity. Okay, so we cross multiply. We're going to have 485 multiplying 343 plus Vs, then everything equal to, so let me try to multiply. So we're going to have 512 multiplied by 343, and that is going to give us this particular figure. Okay, so the figure that we have here is, this is supposed to be 175,616. So what is 485 multiplied by 343? 343 multiplied by, this is 485. And of course, we're going to have 1,663,5 plus 485 Vs equal to 175,616. Okay, so we're going to have something like, this is going to be 4, 8, 5, then S equal to 175,616 minus 166,355. Let's try to see if what we have done is correct. If we subtract that, what are we going to get? Okay, so we're getting something like this 485 Vs equal to, this is 9, sorry, this is supposed to be 9,261 over 485 over 485 divided by 485, and of course our Vs is equal to 19.09 meters per second. Okay, so from here I'm going to wrap this. We know that we use this relationship here. So V, the power 2 is equal to U power 2 plus 2AH. And of course we have, okay, let me try to make everything easy. we make h the subject. So of course this is going to be v squared equal to, we know that this is 0, so this guy is going to come out. We're going to have 2a h over 2a over 2a. You cancel this. H is equal to v to the power 2 over 2a. Now h, we have our v is 19.09 to the power 2 over, then 2, remember the acceleration was given, it was 9.8. So in this case, what is going to be our answer? So it's 19.09 to the power 2 divided by, this is 2 multiplied by 9.8. And our distance is simply 8.59 meters. And of course, this happens to be our final answer. So this is just how you go about solving questions under Doppler effect. If you have enjoyed this video, don't forget to subscribe, and also don't forget to hit the like button and also share. Thank you so much.